For any given function, the derivative of the function is either positive, greater than 0, negative, less than 0, or equal to 0. And for any given function, the second derivative, assuming it has one, is either greater than 0, less than 0, or equal to 0. And when we connect these things, there's some things we can know about the original function just by knowing some facts about the derivative and the second derivative. When both are positive, then the function is increasing, and it's increasing because the derivative is positive, and concave up. It's concave up because the second derivative is positive. When the derivative is positive, but the function is negative, well, because the derivative is positive, then the function is increasing. Because the second derivative is negative, the function would be concave down. When the derivative is positive, we know again that the function is increasing. And when the second derivative equals 0, then we have what is called an inflection point, potentially. Right? It's potential or possible there's an inflection point when the second derivative, well, since it's increasing, you will have an inflection point. And by an inflection point, what we mean is there's a change in concavity. It might be changing from concave up to concave down, or vice versa. Let's look at a graph. Let's consider again y equals x cubed, which is concave down to x equals 0, and then changes to concave up. X equals 0 is the inflection point because the graph changes from concave down to concave up there. And at that point, that's where the second derivative equals 0. Now, when the first derivative is negative, what that always tells us is that the function is decreasing. And when the function is decreasing, but the second derivative is positive, we know that it's concave up. When the second derivative is negative, we know that the graph is concave down. And when the function is decreasing and the second derivative equals 0, we know that we have an inflection point. We know that we have an inflection point there. Finally, whenever the derivative equals 0, if the second derivative is positive and the derivative equals 0, then the graph is going to have this kind of shape there. And that's where the first derivative equals 0. And so you must have a relative, that's concave down. Let's change this graph. The second derivative is positive, so the graph is concave up. The derivative equals 0, so you have a horizontal tangent there. So besides being concave up, you'll have what's called a relative minimum. You must have a low point on your graph when the derivative is 0 and the second derivative is positive. Also notice that the slopes would change, I'll do them in red on our graph, from being negative to being positive. Second case, when the derivative equals 0, but the second derivative is negative, then the graph is concave down. The tangent line would be horizontal, so you will have a relative maximum there. Also notice that in this kind of situation, and again I'll do it in red, the slopes of the tangent lines are changing from being positive to becoming negative. Finally, if both the derivative and the second derivative are negative, then that means the function levels off, right? And you have a possible inflection point. It doesn't have to be an inflection point at that case. There might not be a change of concavity. Right, so x cubed would be an example where you do have an inflection point at 0, but one where you don't have an inflection point would be if the original function is just a constant. Its derivative would be 0. Its second derivative would be 0. So here's the graph of y equals 2. There is no inflection point at, say, 1. It's possible, but there just simply isn't one. So there's some more to function analysis. We'll define some terms for the remainder of this video. Critical points. When we're talking about critical points or critical values, what we mean are endpoints if we have a closed interval. So endpoints on a closed interval. Are critical points. The other critical points is when the derivative equals 0, or where the derivative does not exist. These are called critical points for any function. This doesn't come up a lot, but just to be aware, a stationary point is simply a point where the derivative equals 0, or there's a horizontal tangent. Third, we have what are called relative minimums. These would be minimums that occur on an interval. So let's look at this graphically and consider the features. You could have a graph that does something like this. And just for argument's sake, we'll say at x equals -3, this point would be a relative minimum on this graph. It's relative because if we look from, say, -5 to -1, on that interval it is the minimum, but for the entire graph it is not the minimum. So if we want to look in a certain context, it is a minimum though. The other thing to notice about what's happening at relative minimums, I'll illustrate the first part in red. At a relative minimum there will be a horizontal tangent, which means the derivative will equal 0, and the derivative has changed from being negative before it to positive after it, right? The slopes of the tangents are negative before the minimum and positive after it. That's what happens at a relative minimum. It switches, the derivative switches or changes from negative to positive. The other thing that's true at a relative minimum is the graph would be concave up, so the second derivative would have to be positive at that point. The relative maximum is very similar. Right? A lot of the features are related. A relative maximum of a graph, and this would also be true of absolute maximums. You can see a graph that looks something like this. It has two relative maximums, the one on the right and the one on the left. And we'll talk about, just for this sake, this point right here. This is both a relative maximum, because on the interval, say -5 to -1, it is the maximum. It's also the absolute maximum, because it is the absolutely highest point of this entire function. Some things to notice about the absolute maximum. At the absolute maximum, the derivative equals 0, and it changes from positive, because the slopes of the tangent lines are positive to the left of it, to negative, because they're negative slopes to the right of it. The second thing to note is that the second derivative at a relative or absolute maximum will be negative, because the graph will be concave down. Finally, we've already discussed this. Recall that inflection points are points where the second derivative equals 0 or fails to exist, and it changes signs. Right? So a second derivative will change signs from positive to negative or negative to positive when you have an inflection point, because that's when the concavity changes from concave up to concave down, or vice versa. In the final video for this section, we will look at some example problems regarding function analysis.